Now we're going to look at some other identities that allow us to evaluate trig functions for angles that aren't on the unit circle. We've spent a lot of time talking about the 30 degrees, 45 degrees, 60 degrees, but we haven't really looked at angles like 15 or 75. And one of the reasons is because that's difficult to do unless you're using these formulas. The idea behind this concept is that we're going to learn how to evaluate something like cosine of 15 degrees by breaking it down as the sum or difference of two other angles that are on the unit circle. Cosine of 60 and cosine of 45 are both angles we can evaluate using the unit circle. So if we think of 15 as 60 minus 45, we're going to use the formulas on the next slide to break it down using those computations instead. So here are the formulas we use for sum and difference computations. They are different whether it's cosine, sine, or tangent that we're working with. But it's also important to note that we have a lot of flexibility to choose different numbers for these. For example, if I was trying to do something like cosine of 75 degrees, we just need to pick two angles that either add or subtract to 75 using numbers off of the unit circle. So if you pay attention to the angles that we have in degree form, I could pick 30 plus 45 because those would add up to 75. However, I could also pick something like 135 minus 60. That would also equal 75. So there are lots of choices you can make for these problems. Just make sure that you're using the angles on the unit circle so that we can actually apply the formula and then compute the angles that show up in it. It is also important to pay attention to the use of plus or minus compared with minus or plus. What I'm saying is that if you pick two angles like 30 plus 45 for the two numbers that you chose, if the angles you picked add up together, then on this side, make sure you keep using the symbol that's on the top. So you would be subtracting for this side of the formula. And vice versa. If you picked two angles that subtract, like the example I gave of 135 minus 60, then on the other side of the formula, you would be using the bottom one. So you would have a plus between these two expressions. The sine and the cosine ones are definitely the easiest to evaluate, so we'll start off by focusing on those. The tangent formula doesn't seem much different, but it does require a lot of extra work because of the rationalizing process. So we'll look at those later. Here's our first example. We're going to evaluate cosine of 15, which I started off on the earlier slide to show you the concept, but now we're going to finish and actually apply the formula to get the final answer from it. So one combination of angles you can use from the unit circle would be the 60 minus 45 that I showed earlier. So I'm going to break down 15 degrees as 60 degrees minus 45 degrees. Next, we need to compare this to the formula on the previous slide. So since the angles I chose were to do 60 minus 45, and this is a cosine function, I'm using the top set of formulas here. Everywhere that I see an x, I need to plug in 60 because that was my first angle that I chose. So 60 is going to go in these two locations. And everywhere that I see a y, I'm going to replace that with 45 because 45 was the second angle that I chose for this formula. And then since I picked the minus symbol, I picked two angles that subtracted the given number, so that was the bottom plus or minus. I need to use a plus on the other side of the formula. So now I have a series of trig functions that we can evaluate without using a calculator. We couldn't have done cosine of 15 before, but cosine of 60 and cosine of 45, those are all values we can do from our unit circle instead. So we just want to evaluate each of these separately. Cosine of 60 is equal to 1/2. Cosine of 45 is equal to square root of 2 over 2. And notice that those two trig functions were being multiplied together, so these two should be multiplied together. Then there's a plus sign. Sine of 60 degrees is equal to square root of 3 over 2. And sine of 45 degrees is equal to square root of 2 over 2. So make sure you can do those without a calculator. And then the rules for multiplying fractions together, you do top times top. 1 times square root of 2 is square root of 2. And in the bottom, 2 times 2 is 4. For the other fractions, we have square root of 3 times square root of 2. Since both of these numbers are inside of radicals, you can multiply those together to get square root of 6. And then in the bottom, 2 times 2 is 4 again. Now these two fractions actually have a common denominator, so then I would expect you to combine them into one fraction that says square root of 2 plus square root of 6 all over 4. Some calculators might be able to spit out answers that look like this, but if you don't actually go through the process of doing this on your own, you may find that it rearranges things in different ways. And on any tests, I would be having you guys do them without a calculator anyways. So you definitely don't want to rely on that for this section. So now let's look at one in radian mode instead. It's really easy to pick two degree measurements that add or subtract to the given value. But once you change it to a radian measurement like 5 pi over 12, this gets a little bit trickier. So now let's look at our unit circle for reference. We're trying to find two numbers that add or subtract to give us the 5 pi over 12 value. But the problem with adding and subtracting fractions is you need a common denominator before you can add the numbers. So what I've done is I've rewritten these angles going around the unit circle with a denominator of 12. So I took this first fraction and I multiplied the top and bottom by 2 to get 2 pi over 12. The next fraction, I had to multiply top and bottom by 3 to get a denominator of 12. Next fraction, I had to multiply top and bottom by 4. Next one by 6 over 6. And you can keep going around if you need to, but right here I have shown enough to get a couple numbers that will add up to 5 pi over 12, because now that I have a common denominator, it's easier to recognize that 2 pi over 12 plus 3 pi over 12 would equal 5 pi over 12. Now for these two selections, you'll probably still want to write them in the form pi over 6 and pi over 4. I just did this for help in picking which angles I should be using. So since I made the choice pi over 6 plus pi over 4, again, we just need to apply the formula correctly. So everywhere I see an x this time, I'm going to write pi over 6. Everywhere that I see a y this time, I'm going to write pi over 4. And then since I picked two angles that add together, I'm going to have a minus sign on the other side of the formula. So here's where we are after applying the formula to the angles we chose. Next, we just need to go ahead and actually evaluate the individual trig functions we've broken down here. So this should be done without a calculator again. Cosine of pi over 6 will equal square root of 3 over 2. Cosine of pi over 4 would equal square root of 2 over 2. And then for the sines, we're looking at the y coordinates of the unit circle now. So the sine of pi over 6 is 1/2. And sine of pi over 4 is square root of 2 over 2. Next, we just want to multiply the fractions and then combine them into 1. So if you have a square root times a square root, you can multiply the numbers inside together normally. And then if you're just multiplying whole numbers like 2 times 2, go ahead and do that normally. For the other fraction, 1 times square root of 2 is square root of 2. And 2 times 2 is 4 again. These have a common denominator, so we'll just combine them into one fraction. Now for one last example where we're actually going to look at applying the formula backwards in a way. So this time what I see is what appears to be the right-hand side of the formulas. We have a sine function times a cosine, and then either a plus or a minus, and then another pair of functions. And they have asked us to write this big expression as a sine or cosine function of a single angle instead, because right now I have two different angles in the problem. So what we want to do is compare this to our sum and difference formulas. Notice that this one had sine times cosine, not cosine times cosine. So right now, I know that it's one of these, either the plus or the minus, for a sine function. The next thing we need to pay attention to is that if they were adding the two products, the sine times cosine and the cosine times sine, then I would have the same symbol on the other side. So I would take the two different angles and I would add them together. If they have a minus, then I would be subtracting those two angles. Well, our problem had a plus, so then we said we know it's a sine function, and we said we know that the sign stays the same, so we're going to be adding. And the actual numbers they use, this is the first time I'm actually looking at them now, it's 22 and 13. These are numbers that we do not have on the unit circle, so they wouldn't normally be as much use to us unless we have a calculator. But since I've rewritten the formula as sine of 22 plus 13, well, these two numbers can just be added together. So 22 plus 13 would be equal to 35 degrees. And now we've done what they've asked for. We have taken this big expression and rewritten it as just a single angle with a single trig function, sine of 35 degrees. Sometimes the problem may even give you a number here that you can evaluate from the unit circle. It might have come out to something like 45 degrees, in which case you could even evaluate the sine of 45 from there and say that the answer is root 2 over 2. So this was just an example of applying those sum and difference formulas, but from the right side to the left side instead of vice versa. And that's it for the notes on this section.